Hello everyone, my name is Snehal Jain, and as a part of the virtual ICRA 2020 conference, I'll be presenting a soft gripper with retractable nails for advanced grasping and manipulation. Recent advances in soft robotics has led to the development of several soft grippers and compliant end effectors. Compared to traditional rigid grippers, these soft grippers can adapt to a wider range of payloads and are becoming increasingly popular for dynamic industrial environments. However, for tasks requiring high precision and repeatability, traditional grippers designed with rigid constraints remain widely used. Pneumatic soft grippers using compressed air actuation are often bulky by design. Most pneumatic soft grippers operate by enclosing or wrapping around the payload, as seen in the images on your right. This makes them unsuitable for grasping tasks in confined or cluttered environments and also for lifting thin items from flat surfaces. To solve these challenges, few research groups have developed bio-inspired soft grippers with suction cups and enhanced adhesion. While these grippers are capable of lifting thin flat items such as paper, their grasp reliability largely depends on the contact area as well as the surface finish of the object to be grasped. Nails or thin fingertips have been integrated into both rigid and soft grippers, and their positive effects on tasks requiring precision grasps are well documented. Grippers with rigid fingernails require the nails to be precisely positioned with respect to the payload for successful and secure pinch grasps. This usually requires end effector position control and specific grasping sequences. In this study, we present the design of pneumatically actuated compliant fingernails. Additionally, a soft gripper has been modified and the novel fingernails are integrated with it to highlight the enhancements and simplified pinch grasping that the fingernails provide. The soft gripper used in this study is based on a multi-material gripper developed previously by our group. The soft palm, highlighted by the drawings shown, can be folded in using vacuum in a manner similar to the human palm. Previously, the constrained finger assembly only allowed for parallel grip configuration. In this study, we modified the palm to allow for the finger orientations to be changed. This enables easy switching between centered grip and parallel grip configurations. The fingers consist of a hybrid structure that collapses in an anisotropic manner under vacuum to create a bending motion. The gray regions in the cross-section image highlight the wedges that tailor the deformation of the finger. Each finger consists of two pneumatic sections. One, a vacuum section for the finger bending highlighted in cyan in the cross-section image, and another for the nail actuation highlighted in yellow in the cross-section image. The fingertip wedge houses a bidirectional telescopic mechanism. The mechanism can be actuated in the direction shown by the red arrow by applying compressed air or vacuum through the channel. To allow for modularity, the nail mechanism is designed as a standalone telescopic structure as shown in the bottom right image that can be easily fitted into or removed from the fingertip wedge. To fabricate the gripper fingers and palm, the respective wedges and skins are casted separately using FDM printed molds and off-the-shelf RTV silicones. The wedges are then assembled inside the skins. The skin and wedges are fixed together by adding more silicone to slits located on top and bottom of the skins. Silicone tubes for fingers, palm, and nail actuation are added to the finger base, palm base, and fingertip respectively. 3D printed interfaces are then casted to the finger base and palm sides. Another interface for integrating the gripper with robotic arm end effectors is casted to the base of the palm. The parts of the telescopic nail structure are 3D printed using a polyjet printer. The grooves on the nail and the channel are lubricated using silicone oil, and the nail is then inserted into the channel. Custom-shaped O-rings are casted, shown in red in the image to the right. These O-rings are inserted inside the channel to create a seal. The telescopic nail structures are then slotted into the fingertips. The bidirectional pneumatic actuation, as shown in the video, is achieved by using a pump with both positive and negative outputs connected to a selector valve. In order to study the grasp forces of the nails and gripper, systematic experiments were conducted. In one experiment, thin plates of different shapes and chamfer angles alpha were fixed to a load cell. The plates were grasped using the gripper such that the extended nails only were in contact with the plate edges. The gripper was then moved away from the plates until the plate was released from its grasp. The average load cell values have been plotted in the figure shown below. The nails were able to generate forces of around 250 grams or 2.5 newtons for smaller chamfer angles. It was also observed that across all plate shapes, as the chamfer angle increased, the grasp forces of the nails decreased. In another similar experiment, 3D objects of cylindrical or spherical geometry were attached to the load cell. The gripper then grasped objects in both parallel and centered grip configurations. The plot on the right shows the forces generated by the gripper over time. In the plot legend, SC indicates the sphere in centered grip, SP indicates sphere in parallel grip, and CP indicates cylinder in parallel grip. It can be seen that the gripper can generate forces close to 30 newtons for cylindrical objects. Also, comparing the SP and SC curves shows that for spheres, a centered grip configuration generates higher grasping forces compared to parallel grip configurations. This claim is also supported by the image on the top right, which highlights the contrast in contact effort of the soft gripper on spheres between centered and parallel configurations. To highlight the advantage of nails for grasping thin items from flat surfaces, the gripper was mounted on a UR10 robotic arm and the system was programmed to move and grasp 3D printed cards of varying thicknesses. The cards were placed on a flat surface and a simple linear top-down gripper approach was used. The plot in the slide shows the gripper's success rate for the tested thicknesses. Without the fingernails, the gripper was able to pick cards of significant thicknesses with great repeatability. However, for cards of 3 to 4 mm thickness, the grasps using the gripper alone were either not reliable or not repeatable. For thin cards below 3 mm, the soft fingertips were not able to generate enough contact area for grasping. For cards thinner than 3 mm, the same programmed grasping was tested, but this time with the nails extended for the pinch grasps. For cards of 1 mm thickness or above, the nails were able to grasp with 100% repeatability. The gripper also showed high success for grasping flexible cards having soft modulus. It was also seen that the gripper nails assisted in grasping cards of just 200 micron thickness with 60% repeatability. The grasping action of the retractable nails is highly compliant due to the nature of the pneumatic telescopic mechanism used to actuate the nails. When the nails are extended using pressures less than or equal to 40 kilopascals, the telescopic mechanism behaves like a compliant system. To explain in detail, unlike rigid nails, these nails can be retracted passively when the compressed air actuation force is countered by a larger opposing force. This passive behavior allows for the nails to automatically adjust their extended lengths as the fingers bend against flat surfaces. The compliant fingernails can self-level with the flat surfaces as shown by the two videos, allowing for successful grasping without the need for accurate or strict position control. To conclude, a reconfigurable soft gripper design with retractable nails has been presented. The enhancements of soft bending actuators due to retractable nails and a reconfigurable palm have been highlighted through experimentation. Along with the capability to grasp thin items of 200 micron thickness from flat surfaces, the gripper is capable of grasping a wide range of payloads. The compliant nail mechanism allows for a simplified approach to precision grasping of thin items from flat surfaces. Thank you for watching this presentation. I'd also like to thank the SUTD Digital Manufacturing and Design Center, as well as the Agency for Science, Technology and Research for funding and supporting this work. If you are interested in our work or have any questions, please feel free to reach out to us at the contact information provided.